Hello, everyone. I think it's the time to start the session. So first of all, I would like to welcome you all in the fourth talk of our distinguished speakers under Saudi Aramco Cybersecurity Chair. Today, we are glad to host a very interesting talk by Professor Thuraisingham. Professor Bhavani Thuraisingham is the founder chair, professor of computer science, and the executive director of the Cybersecurity Research and Education Institute at the University of Texas at Dallas. She's also a visiting research fellow at King's College, University of London, and also an elected fellow of the ACM, IEEE, the AAAS, the NAI, and the BCS. Her research work includes cybersecurity and AI data science for the past 36 years. She has received several awards, including the IEEE CS 1997 Technical Achievement Award, the ACM SIG-AC 2010 Outstanding Contribution Award, and many others. Her 41 years career includes industry experience, such as Honeywell, Federal Research Laboratory, such as MIT RES, US government, NSF, and the US academia. I'm sorry, the light goes off automatically after some inactivity. Her work has been published in 130 journal articles, 300 conference papers, 180 keynote and featured addresses. She has also published 7 US patents, 15 books, as well as technology transfer of the research to commercial products and operational systems. She received her PhD from the University of Wales, UK, and the prestigious higher degree of doctorate from the University of Bristol, UK. Just to orient those who are attending this session for the first time, we will divide the talk into 2 sessions. In the first part, speaker will present in 40-45 minutes her talk. And the last 10-15 minutes, we will give you the opportunity to ask questions from the speaker. So I'll be glad to moderate this session. And with this, I will now invite Professor Bhavani to take over the session, please.
Thank you very much, Professor Min Allah, for giving me the opportunity to present this distinguished webinar at the Imam Abdulrahman bin Faisal University in Saudi Arabia. And I am truly honored. And I'm going to now share my screen. And if it is okay, while I'm presenting, I will mute. Right, I would like to mute my video if possible. I don't see that right now. Okay, I'm sorry, I'm unable to mute the video. Okay, so, oh yeah. Yes, so I would, and then I will turn it on, the video at the end. Okay, so my talk is going to be integrating machine learning and cybersecurity with applications in the Internet of Transportation and infrastructures. So this is the outline of my presentation. So it's going to be in 3 parts. The part 1 is going to integrate cybersecurity with AI, machine learning, data science. So I use the word artificial intelligence, machine learning, and data science interchangeably in this presentation. There are, of course, some minor differences, and I call it SecAI. And so the topics I will be discussing are big data security and privacy, privacy-aware quantified self, data science, ML, AI for cybersecurity applications, securing data science, ML, AI techniques, trustworthy machine learning AI, and that's part 1. Part 2, I'll be talking about security and privacy for the Internet of Things, in particular, Internet of Transportation and infrastructures. And part 3 is going to be the application of part 1 to part 2, and that's application of security and AI for Internet of Transportation and infrastructures. I would like to thank several people, our sponsors, National Science Foundation, Army, Air Force, NASA, NIST, NSA, and my colleagues, Professors Alvaro Cardenas, Murad Kantajulu, Latifa Khan, and our former PhD student Raul Quiñones, and our project coordinator, Ms. Rhonda Walls. The first part is integrating cybersecurity and artificial intelligence for machine learning and data science. So I'm going to give some motivation on data mining. So I also use the word data mining and data science interchangeably, data mining, security, and privacy. So back in 1996, I believe I introduced this idea before many people were talking about it, how data mining could be applied to cybersecurity and what are the privacy considerations. And this was at a keynote address, first at IFIP 11.3 conference in 1996 in Como, Italy, and later at the Pacific Asia Knowledge Discovery Conference in Melbourne, Australia in 1998.
Professor Bhavani,
yes.
We cannot see the slides changing. Can you just maybe something wrong? We see only the first slide still now.
Can you see it now?
No, it's not changing.
Is it because I don't have the, it's never happened before. Can you see it now?
No, still no change.
Let me try to.
Maybe you can share the slides only. Or we can play the slides for you if there is any issue.
Yes, can you play the slides for me?
We can, just hold on.
But I need to stop sharing then. Just a second. Okay, great.
Can you see my screen now?
Yes.
Okay,
so
I'll use the slides for you and you can.
Okay. So it's integrating machine learning and cybersecurity with applications in Internet of Transportation and infrastructures. Next. Right, so it's going to be 3 parts, as I said. Part 1, integrating cybersecurity and machine learning and data science. And I use, as I said, I use the words interchangeably. So we talk big data security and privacy, privacy aware quantified self, data science, machine learning for cybersecurity applications, securing data science, machine learning, AI techniques, trustworthy machine learning. Part 2 is going to be security and privacy for Internet of Things, Internet of Transportation and infrastructures in particular. Part 3 is going to be applying part 1 to part 2. And as I mentioned earlier, a number of people that I would like to thank. Next. Right, so part 1 is integrating cybersecurity and AI machine learning data science. Next. So some motivation. I introduced the idea in data mining, security and privacy at the keynote address, first at IFIP 11.3 conference in Como, Italy, and later at the Pacific Asia Data Mining Conference in 1998. I believe this is where I left off. And so subsequently published, I would say, a landmark paper, and I will tell you why. When I was at NSF in 2002, that's the National Science Foundation, because when you are a program director at NSF and when you write a paper, it spawns a whole new area of research because you are sort of responsible for the funding. And around that time, there was this researcher from IBM Almaden Research Center, and he published a paper on privacy preserving data mining. That is, how do you do data mining, but at the same time maintain privacy? So he had the original data, you add noise, and then you have the noise added data. So let's say your age is 25, you sort of increase it to maybe 26 or decrease to 24 very slightly, so you don't give out your actual age. And then you carry out the data mining with a modified data mining process. But the end result has to be the same, the final result. So that way, privacy is maintained. So we started, when I joined the university in October 2004, we had a PhD student, Dr. Li Liu, a lady, together with Dr. Murad Kantajulu was a co-advisor. We looked at various aspects of privacy preserving data mining, in particular privacy preserving decision trees. and also studied extensively the best way to perturb the data mining, the actual data. So that was in the mid 2000s. But then in the 2013-14, data mining, security and privacy, they were exacerbated because why? Big data and data science. So we are now able to gather lots of data and collect data, store data, and process the data, share data. So privacy becomes more of a problem. So I hosted a National Science Foundation workshop in September 2014 and presented the results to the Interagency Working Group in Washington, D.C. in February 2015, and that spawned a whole new area of research. Next. So the next chart, please. Okay, so at the workshop, the Big Data Management, Security and Privacy, we looked at various aspects. I'll very quickly go through this particular chart. So a lot of technological advances, so we can, as I said, capture, process, analyze large amounts of data for a number of tasks, healthcare, finance, even for cybersecurity. For cybersecurity, we can use the data for authentication, access control, anomaly detection, monitoring the users, and analyze large amounts of data and so on, and also protect from insider threat. So analyzing and integrating data collected on the web, we can identify connections, relationships, and so on. And you can anonymize the collected data, but then by removing the identifiers, but when you link the data together, you could re-identify the individual. That's the major challenge. And even security tasks like authentication, access control, and so on may require detailed information about users, like multi-factor authentication. So this information, if misused or stolen, it can lead to privacy breaches, right? So what did we study at the workshop? We looked at various access control models for big data, privacy enhanced techniques, big data analytics for cybersecurity, and one of the very popular areas is securing machine learning. On the one hand, we can apply machine learning for cybersecurity, like malware analysis, insider threat detection. But what happens if the machine learning techniques are attacked, right? So, instead of giving the outcome that say you have COVID, it will give you the outcome that you have just a common cold or a flu. And that could be disastrous consequences, right? And so that's the challenge that we have. Next. So what we are doing, and I think, I'm waiting for the next chart, Professor. Right. So we developed privacy-aware quantified self. So what is quantified self? The psychologists and sociologists have got something called a quantified self movement. So there's mobile devices, we are all carrying smartphones and so on. But what they are proposing is to use all of the data collected and analyzed to help us. Like, for instance, I like milk chocolates and vanilla ice cream. It would be great if I open the refrigerator and if the system tells me, no, you should not eat it. Now, there is a message on my smartphone that I should not be eating milk chocolates. By the way, I don't keep any milk chocolates in my refrigerator. But in any case, what happens, this sort of information, it could go to my insurance company and I might be denied insurance, right? So for instance, this data that is being collected, they are often shared with other users, and that could provide grave danger. So for example, if data collected by a mobile device like blood glucose levels, it can be used by the insurance company to deny not only my insurance coverage to myself, but also to my son and to my grandchildren. So that could be really a disastrous consequence. And if privacy violations could easily get out of control, data collectors could aggregate financial and health-related data, and they could sell that data to various other groups. There could be lawsuits, psychological damage. And so to address this, we need tools for privacy-aware quantified self. Okay, so the next chart. Right, so this is the picture that we have. We have health-related information, financial data, fitness data, location, and social media. Everything is gathered in our smartphone. It has data collection, data storage, data analytics, data sharing. So this is the data management framework that we have developed. Some of the data encrypted, stored in the cloud, and we use cloud services to access the data. But the main point we are saying, we need policies for data collection, for data storage, for data analytics, as well as for data sharing. So we have policy-based, privacy-aware data management framework. That is what we are developing. Next chart. So here is the policy-aware data collection, storage, analytics. So we have our mobile apps. This is our mobile system, and this is our framework, and policies are governing, and also cloud-based encrypted data store for lots of the data are stored in the cloud and some others in the mobile device. So lots of data being collected. It will not be sufficient to store all of the data. So we envision an encrypted cloud storage component where all the data and less frequently accessed data are pushed to the cloud. So based on access control policies, some local apps on the device will be given access to some of the collected data, and some other cases it can query the cloud through some encrypted query interface. Some cases, like for instance, you may not need to store the weight of a 20-year-old every day, right? Or to weigh a 20-year-old person, because even if a 20-year-old person puts on 5 pounds, it's not going to be so bad. But if a 70-year-old person puts on 5 pounds in a day, that could be taxing to the heart, right? So in some other cases, you may have to delete the data. And that's a major challenge, because when you delete the data, is the data really deleted, right? That's the challenge. So we envision the data sharing and analytics will be carried out using services. And based on the different scenarios, you can encrypt, you can sanitize, you can perturb. So the main thing here is that policies have to govern. You need appropriate policies to collect data, to store data, to analyze data, and to share data. And we are computer scientists, and we are not really qualified to develop policies. So what we do, we have worked with a policy expert at our university, and so she is developing the policies, and we develop the algorithms to enforce the policies. So that's the part on privacy. Next chart. Okay, so now we go to data science, machine learning for cybersecurity applications, right? So what we do, big data stream is joint work with Professor Latifa Khan. So we use past data to build the classification model. We predict the labels of future instances using the model, and that helps with the decision making, right? So you can ask this question, so what's the big deal? This has been done for a long time. The challenge is that we have big data streams, continuously flow of data, very common in our digital world, massive amounts of data. It could be financial data, it could be telecommunication data, it could be network data, and also the concepts are changing, right? So for instance, today it says buy Microsoft, tomorrow buy Google shares, next day buy Apple shares, then buy Facebook shares, and so on, right? Amazon shares. So concepts are changing. So one model will not fit everything. So we build an ensemble of models. And so when the test data comes in, these models are applied. And if it's benign, it goes in, stores in the server. Otherwise, we block and quarantine. Ensemble of models means a collection of models. So when the model is no longer valid, we throw it away. And when the model, and we use the good model. So that is the challenge. That is the major research. And we've published a number of papers. Mahidi Masood was a PhD student and a postdoc, and now he's a professor at the university in Abu Dhabi. And we also, this is a joint work with Professor Jewei Han, a top-notch researcher in data science. Next chart. And so continuing in this, we are working on insider threat detection application, number of applications. We have applied it to malware analysis, and here we are doing it for insider threat. So what is inside the threat? Very briefly, bad people behaving like good people, right, inside a company, and they take all the secrets and send it to the adversary. Similarly, bad malicious processes come into the system and pretend to be good processes, and they collect all the information. They can cause damage, collect all the information and send it to the adversary. So we have developed a variety of algorithms, both supervised algorithms, machine learning, and unsupervised machine learning. Supervised machine learning is essentially, we use support, you can use decision trees, but we have used support vector machines, in particular one class support vector machine. For unsupervised machine learning, that is really, there's really no training and modeling. So what we do here is look at all the sequences, the words that are being typed, and then we build a graph out of it, and then we compress the graph and then try to find patterns. Okay, so our unsupervised algorithm, machine learning, performed much better than our supervised machine learning. That's all. And I can share with you all later on some of the papers that we have written on this topic. Next chart. Okay, so this is sort of shows us a picture of what really happened. So a person here is typing all kinds of stuff. We take I chunks and we extract features. Again, the research here is extracting the appropriate features and, more importantly, building the ensemble of models, collection of models. Bad models, they all vote with each other. They work together, these models, and they vote. If the models are bad, they throw it away. Our learning algorithms, unsupervised graph, as well as supervised, we use support vector machine. So what happens is that when the test data comes in, I+1 chunk, extract features, and then we do the testing. So the process is the same. But again, the challenge here is developing the ensemble and doing this in real time. So this is really the major breakthrough. Because 20 years ago, we were doing something similar, but we didn't really know how to do real-time machine learning. But now we can change these models in real time. Next chart. Okay, so now we move on to the other topic. This is really the hottest topic right now in cybersecurity, and that is what happens if the machine learning techniques are attacked. This could be a disaster, right? Because as I said, instead of saying you've got COVID, the machine learning technique could say, algorithm would say that you have a cold and you will not be given the medication. And as a result, you could die. So what happens? The adversary modifies. So adversary is watching, right? It's watching to see what we are doing, looking at what are our models, what is our data, and they are trying to thwart us, right? By corrupting the data and by changing our models. So for instance, the red squares here are the bad instances. The blue circles or the purple circles here are the good instances. And the line here is the support vector machine boundary. So we have to understand the adversary, right? So the adversary, it's not about concept drift. It's not online learning. Adversary is adapting to avoid being detected. It could be during training time, during testing time. Essentially, it becomes a game playing between us and the adversary. Okay, so what the adversary is trying to do is to push these red squares below the boundary so that they will not be caught. Next chart. Yes, so before we go to our solution, what is it that we are doing, right? What is the attack model? And our paper, this is one of the early papers in the field that was published in the Knowledge Discovery in Database Conference. Example, adversarial attacks. So we have a number of attacks. We looked at two classes, free range attacks and the targeted attack. Just to, because I don't have time to go through the details of this mathematics, but the free range attack is that the adversary can place the data anywhere in the range, right? And targeted attack is really more natural, that sort of mirrors more what happens in the real world. We looked at both these attacks and I'll tell you what our solution. Next chart. So our solution really is to study what the adversary is up to. So this is really the support vector machine original boundary. Black dashed line is a support vector machine boundary. The blue line, so we do all of the research, right? The green circles are the good instances. The red crosses are the bad instances. What we are trying to do, look at these, because the line is here, some of the bad instances, the red crosses, are not being caught, right? So what do? We try to apply game. So we are playing a game with the adversary. So we move this with this dash line to the blue line. Blue line is the new support vector machine. So with the blue line, more of the bad instances are being caught. So that is a challenge. So threat model, test time, deployment, attacker can modify X to X prime, it can add dummy bytes and add good words and so on. But again, the challenge for us is to find out where do we place the blue line. We can move the blue line far away as possible beyond all these green circles. That means all of the bad instances will be caught. But if we move the blue line really far away, we will not have a way to, all the green instances will also show as bad instances. And by doing that, we will have we will have lots of false positives and lots of false negatives. Okay, so our paper was presented actually as early as 2012 in the top conference, ACM Knowledge Discovery Conference. And since then, lots of papers have been published. As I said, this is like one of the top areas right now in cybersecurity, that is adversarial machine learning. And it sort of becomes game playing between us and the adversary. Next chart. Okay, so what are some of the other things, right? So another area is, how do you trust these machine learning algorithms? Because if these machine learning algorithms can be trusted, the problems I mentioned in the previous chart, it may not occur, right? So there's lots of data for computation. We may use third-party servers or our machine learning algorithm. As a result, our machine learning algorithms could be attacked. So one solution is to do this machine learning in hardware. What does that mean? We can use the Intel SGX platform and use that platform to execute these machine learning algorithms, and it could provide us with some protection. Although there is some research right now to show that this may not be entirely secure. And the last part, I was on a panel some months ago, and there was this lady, a professor from University of Oxford in England, and she was talking about applying formal methods for machine learning so that the machine learning algorithms, the software, meets the specifications. So these are all some of the solutions that are being proposed. Next chart. And so what I show here is the trustworthy analytics and the SGX platform. So all I want to say here is that the data, right, on the machine learning algorithms are being executed in the SGX and enclave memory. It's a secure location. And this way we can provide some protection. So the machine learning algorithms may not be attacked, may not be. As a result, it can provide some useful results. Okay, so next chart. So next I talk about part 2, which is security and privacy for the Internet of Transportation. So what's Internet of Things? Internet of Things is that our cell phones are connected to our what? Are connected to our television, to our Amazon carts, to our coffee maker or tea maker, to our clock, and everything is connected. And they're all talking to each other with sensors. Imagine if one of these gadgets is attacked, the whole system would crash. Similarly, in a transportation, there's Internet of Financial Things, Internet of Medical Things, Internet of Manufacturing Things, and there's Internet of Transportation Things. Internet of Transportation, cars are talking to each other, to the trains, to the trucks, and to the roadworks. The whole idea is by communication, you can avoid accidents and you can provide better routes, better services. Next chart. So this whole Internet of Transportation, major implications in the transportation industry. Autonomous vehicles improve day-to-day activities, delivering packages, improving traffic, transportation of goods in the US. In the US only, the transportation carries about 63.3. The trucks carry 63.3% of the goods. So autonomous vehicles are not limited to just ground. They also include aerial, like drones, and sea vehicles, right? So levels of automation will range from 0 to 5, right? Ground vehicles, it's about 2, like cars, and aerial vehicles automation is 4. Big companies like General Motors, they have presented $728 million in R&D in 2018. It's increased to $1 billion in 2019 and more in 2020 and beyond. And there's great potential in autonomous vehicles, and the improvements it can do transportation is really great, but there are security and privacy concerns. Next. So what are the security concerns? So autonomous vehicles, right, their environment, they use a variety of sensors like camera, GPS, and so on, LiDAR, radar. So previous research by us and others, it's shown that the sensors are susceptible to malicious tampering, like the IMU, which is the inertial measurement units, are susceptible to sound waves, and GPS receptors are susceptible to spoofing. Vehicles should verify the veracity. Okay, so like what happens in this picture, sensor-based, right? They're all communicating with sensors. And then inherited issues. So we know that sensors are susceptible to GPS spoofing and transduction attacks, the manipulated environment, physical signals. And so what are the defenses? Classical cybersecurity techniques like memory protection and cryptography, they work to some extent, but we need, right, for sensors, and for the special types of attacks, we need new types of solutions. And because of the real-time constraints, AVs act upon sensor data without any form of verification, right? So real-time intervention is really important. Next chart. Okay, so what have we done? We have developed, this is just, we have not applied AI yet. So we have developed a physics-based anomaly detector. So we have built a reference monitor. What is a reference monitor? That is the part of a system that controls all the security aspects, access control, the whole lot. So based on physics, and I'll show you in my next chart, right? Anomaly detection algorithm, we call it PBAD, for ground and aerial vehicles. The algorithm will consist of 3 parts. You will build a model offline, right, of the autonomous vehicle's physical properties, implementing a tool online to monitor expected and observed behavior to detect anomalies. And then we raise an alarm if significant residual differences exist between the executions. So offline pre-processing, building the model, online verification, right? And that is implementing the online tool. And then we do the anomaly detection. So next chart. So you could ask the question, what's the big deal, right? You're saying what we have been saying for a long time. Couple of challenges. One is that you have to build the model, and you need control engineers, cyber physical systems specialists. So my colleague, Dr. Alvaro Cardenas, is an expert. I'm a computer scientist. He's a control systems specialist with cybersecurity. So he built the model, and that's what we show the picture in the right-hand side. You've got to figure out what is the state, what are the inputs, and what are the X, Y, Z axis, moments of inertia. So he built the model. AV invariants are calculated using well-known, again, nonlinear models for aerial and ground vehicles. And he used the accelerometer, gyroscope, and magnetometer sensor data for X, Y, Z axis, and so on. Online stage, and again, at this time, we didn't use machine learning. We used extended Kalman filter. It's used to predict the AV's physical behavior by estimating unknown parameters. And then the algorithm is divided into 2 sections. You predict and correct the estimation before it's compared to the sensor data. So the anomaly detection part, we use the CUSUM, that's the statistical algorithm, to detect persistent attacks. The alarm is raised if residual differences is larger than the predefined threshold. Again, we are using some traditional methods, right? Because again, it's a new environment. So what we are doing here is known techniques for a new environment. We are not using machine learning yet. Next chart. So a physical implementation, you can see we have used for drones as well as for cars, aerial AV Intel ready-to-fly drone controller, PX4 flight controller. It focused on detecting GPS spoofing and gyroscope attacks. Spoofing was in 0.2 seconds and gyroscope 1.5 seconds. Overhead is 5.4%. For the ground, we used cars for custom built on top of Traxxas Ford Fiesta. The controller was ROS and focused on detecting visual attacks on the camera. So the attacks occurred after 0.1 second and the overhead was about 2.2%. So each threshold produces a probability of false alarms of about 2%, which is quite high. Okay, so the next chart. Right, so that's the security part. What did we do for privacy? So beyond the security of the individuals, right, the transportation sector could greatly benefit from a supporting infrastructure, allows communication between, as I said, vehicles, motion sensors, lampposts, surveillance cameras, and almost everything. Why? Because it can help identify traffic jams and perhaps even it will improve accidents and save lives, vehicle safety, provided there are no attacks, right? If there are attacks, then it could be a real disaster. But in any case, assuming everything goes well, from a user's perspective, it's not so good because there are privacy concerns. I may not want people to know that I smoke in the car. Of course, I don't smoke, or I drink alcohol. Of course, I don't drink, but still, assuming I don't want anyone to see that I'm smoking or drinking and sending those pictures to my insurance companies. Or I may not want where I am in a certain location. I may not want other people to know who I'm visiting, right? So I really want my privacy. So because all of these systems are communicating, privacy could be violated. So legislators, engineers, and scientists should keep privacy concerns in mind. By doing that, you can also promote technology because people will be feel more safe that they are not being monitored and so on, especially by agencies and governments and so on. So they will have more confidence to use the technologies, right? That's the privacy aspects. And we really haven't done much on privacy yet for this particular space. The next one. So now we move on to the third part, applications of part 1 to part 2, right? And so the next chart. So I only have a few more charts and I'd like to have many questions after that. Okay, so what are we doing? Data science, AI for transportation security. Remember what I mentioned earlier. In the first part, I talked about how we are building the big data streams. We have built several algorithms on monitoring, like concept drifts, and also like today we buy Microsoft, tomorrow we are buying Apple, the next day we are buying Facebook. So concepts are changing. We are building an ensemble of models. That's what we did for the first part. For the second part, we only applied Kalman filter and the Kusum algorithm. It's just one model is what we developed. And that may not be sufficient for the transportation applications, right? Because every day the traffic is changing, right? The threats are changing, the traffic is changing, the patterns are changing. It could be raining, it could be sunny the next day. So the one model may not fit everything, right? So that is why we need to build an ensemble of models, and traditional methods, we may not be able to do that. And that is why we are looking at machine learning for transportation. So they are subject to attacks. Again, data is streaming, sensor data is streaming. So as transportation systems go electric, we also need energy conservation, but there are threats to security, and this could cause massive damage, accidents, loss of lives, and so on. So what we are doing, Kalman filter and so on is great, but it's only giving us one model. We need an ensemble of models. So we are taking the models that we built in part 1 and we are applying it to transportation systems, right? Internet of transportation. And what we find is, will those models that we develop of financial and telecommunications data and network data, will that work for transportation systems? And the main question is to understand the nature of the complex transportation data and adapt it, stream analytics techniques, and apply them on the massive amounts of heterogeneous data. Next chart. So that's data science for, or machine learning for, cybersecurity. Remember I talked about adversarial, so that research is ongoing right now. This research that I show in this chart, we are just beginning. Remember I talked about adversarial machine learning, and again, as I said, this is the hottest, most popular topic right now in cybersecurity, or one of the most popular topics. So Internet of Transportation systems, without a doubt, they rely on artificial intelligence, machine learning, right? Machine learning is going to help to provide optimum directions, driving without a human in the loop, autonomous vehicles, right? Driverless vehicles. It's relying mostly on AI and machine learning. But then what happens? Adversary will be able to learn the models. So these machine learning techniques could be attacked, right? So if these machine learning techniques are attacked, there could be even more chaos, right? Instead of providing some order, it could be total chaos. And so adversary is trying to learn what we are doing, and the vehicle's machine learning models, and it's trying to thwart the model. So therefore, the learning algorithms have to adapt to thwart the adversary's actions. Eventually, it becomes game playing between the adversary and the vehicle's machine learning algorithms. So again, the questions are, what are the appropriate games here? There are zero-sum games, Bayesian games, Stackelberg games, and so on. So we've got to understand the data. And the research on this topic is just beginning. Okay, so we are beginning the research on adversarial machine learning for transportation systems. And the next one. Okay, so this is, remember I talked about privacy and I showed about our smartphone, all the data that is being collected, like our healthcare data, social media data, and so on. Yes, we are proposing something similar. And by the way, we haven't started this work yet. This is something that we are planning to do for the future. And so instead of a smartphone, we have some kind of a gadget inside our car. And that's for data collection, data storage, data analytics, and data sharing. And the data is not our healthcare data. It's more the radar, the GPS, the cameras, the LIDAR, the ultrasonic sensors. And so essentially what we are proposing to develop is a policy-based, privacy-aware autonomous vehicle. And some of the data could be encrypted and stored in the cloud storage, and using cloud-based services, we could collect the data, access the data. One point I want to mention here, which I haven't shown in this picture, I say cloud storage, but remember, for Internet of Things, it's not just the cloud. There's also this whole concept of edge, EDGE, that is being developed. Edge is sort of like a mini cloud, but that is stored near the data, right? Because everything is real time, sensor data. So you really don't have time to go to the cloud. That could be stored in a different state or in a different country. So you want to process the data close to where the IoT is, right? There are many, many subsystems connected. So you have the edge, and then of course you will have the cloud. So that's the direction that we are taking. And my last chart, next one. Right, so the directions, right, so we talked about developments in integrating cybersecurity and AI. I talked about privacy, and then I talked about how data science, machine learning could be applied for AI, in particular, insider threat detection. Then I also talked about security for AI, what happens if the machine learning techniques are attacked, total disaster. And then I talked about privacy-aware healthcare to manage one's life's activities, privacy-aware quantified self. And now with the Internet of Things, include the Internet of Transportation, security privacy solutions are being developed. They are mainly physics-based solutions using traditional approaches like Kalman filters. But when you have driverless cars, right, more and more AVs will use machine learning AI techniques. So the question is, how can we develop AI solutions for detecting malware in autonomous vehicles? And what happens if the machine learning techniques are attacked? And then I talked about very briefly about how can we develop a policy-based privacy-aware framework for Internet of Transportation, right? That's the picture with the car. And then last of all, is it possible to bring in an Intel SGX platform into this picture, right, for trustworthy machine learning, so that machine learning algorithms could be executed in hardware in a secure location? And of course, right, data is coming in all directions. So can we apply formal methods? These are questions, right? So what I'm saying is I presented a lot of topics, right? Security for AI, AI for security, And what happens if the AI techniques are attacked? What about the privacy considerations? Then I gave an application in Internet of Transportations, and how can we enhance Internet of Transportation security and privacy with AI? Now, this is sort of what I've presented in all the questions. We could have about 10 PhD theses, hopefully maybe between your university, Imam Abdulrahman bin Faisal University, and University of Texas at Dallas, right? We could work on so many exciting research problems. Next chart. That's the last one. Acknowledgements, right? So Professor Alvaro Cardenas is a top expert in cyber-physical system security. He was with us, but because of two-body problem, he's joined the University of California, Santa Cruz. Professor Murad Kantajulu, he also just became an ACM fellow. Sorry, he just became an IEEE fellow. He is a top expert in adversarial machine learning. And Professor Latifa Khan also just became an IEEE fellow, and he's a top expert in data science, machine learning for cybersecurity. And by the way, Professor Latifa Khan is very interested in giving lectures, and he has visited the Kingdom of Saudi Arabia quite a few times to give talks as well as to visit religious sites. So he's very excited I'm giving this talk because he'd like to give some talks himself. And then our PhD student, Dr. Raul Quinones in cyber-physical systems and Internet of Transportation security. And Ms. Rhonda Walls, who is our project coordinator, she helps us with a lot of our work. And so we are grateful to everyone. And so this is my presentation. And now I think, sorry about that little thing. I don't know what happened. But anyway, now I'll be happy to answer questions. And again, thank you very much for inviting me. So Professor Min Allah, now you can ask me any questions. The audience can ask me questions. We have about, 15 minutes? Yeah, Professor Nasro, yeah.
Yes, so the first question we received from the attendees, and the first one says, which certificate you recommend to have for cybersecurity career?
Okay, so it depends the career that you want to have, right? So of course, if you want to have a research career, then yes, BS, MS, PhD, and try to write those research publications, the top tier conferences, the top tier journals, IEEE transactions on dependable and secure computing, ACM transactions on security and privacy, and so on. But there are also many certifications. Now because I came from industry and I work for the Federal Lab, I work for MITRE Corporation, then the National Science Foundation. So I have both in the sense that I did the CISSP, that is the Cybersecurity Certified Information System Security Professional. I passed it in 2010. So, and I maintained it for 6 years. Unfortunately, I didn't extend it. That is very good if you want to work as a cybersecurity expert for a company, helping them with their cybersecurity needs and so on. Or if you want to be a top person in CISO, which is a Chief Information Security Officer, you will need those qualifications. If you want to be more hands-on in cybersecurity, then I would look at SANS. That is an institute, I think, SANS Institute. They have a variety of courses. In fact, I've taken some of their courses, like I'm a certified, general certified, GX certified forensics examiner. Because I started teaching computer forensics and some of the practical aspects, I wasn't as familiar, right? So sometimes being professors, we focus on the research. So what I do, if I need some experience, then I go and take those practical courses and do the forensics myself. And then I improved on my teaching. So if you want to be really a practical cybersecurity person for a company, then I will recommend for you to take these courses with SANS. So, and there are various other courses specifically targeted Cisco and Microsoft and so on. But in general, I would say CISP, CISSP, SANS, cybersecurity. And again, if you want to get into research, just focus on your BS, MS, PhD, and then do the research. So these are some of the suggestions. I hope, Professor Min Allah, that it would be helpful for the audience.
Thanks. Yeah, perfectly fine. So the next question says, what is the best platform that can be used to integrate machine learning with cybersecurity systems?
Okay. That is a good question. So what is the best platform, right? Remember, when you are applying machine learning to cybersecurity problems, you are really working with lots and lots of data. So essentially, you are working with big data, massive amounts of data. Okay, so there are two questions. What are the machine learning algorithms themselves? And then how do you scale them? So if you look at the cloud computing platforms like Amazon and Google and IBM, they are all like Amazon AWS, right? They are providing machine learning services. So what you can do is use the Amazon platform for scaling and use their machine learning services. And then you can also plug and play, put in your service, your machine learning algorithms. And your machine learning algorithms, you can develop from scratch, or you can use a number of algorithms like Weka that's developed in New Zealand. We use that for a lot of our algorithms, but that's not commercial quality. But for research purposes, right, you can use the Weka algorithms and then use the Amazon services for scaling. So again, cloud is important because that's providing the scale for you, right? Then you can also use other platforms like Spark, right? S-P-A-R-K, that came out of UC Berkeley, which is now everybody is using for cloud platforms for scalability. So what we have done is we develop our machine learning algorithms, but to use it in a commercial environment, it has to scale. And so then what we do is use the cloud and re-implement our algorithms so that it can scale. So we use our own cloud, but today, of course, we use the Amazon's cloud or Google Cloud or Microsoft's cloud, IBM cloud. They all provide capabilities for you to plug in your machine learning, right? So there's machine learning and then there's cybersecurity. So that's the machine learning. Then you can apply it for any number of applications, including cybersecurity. But another thing for cybersecurity, a challenge is how do you get the data, cybersecurity data? Because right now we use the data that's available in websites because no companies are going to share their attack data. Or I won't say no companies are reluctant to share their attack data. And governments also don't want to share the data. And that's really for, confidentiality purposes, right? So getting the data for us has been a challenge. And much of the data we are getting is from people who can share, who are willing to share with us, or whatever is out there in the public domain. So I hope that helps answer the question.
Yeah, thanks, Professor. This is the last question we have received from the participants. After this, we will go live. We will take questions from the audience. But this question, let me ask the question. Maybe you can answer in 1-2 minutes. Otherwise, we are running out of time. So how to implement machine learning in cybersecurity with applications in Internet of Transportation and infrastructures? The last question, please.
Okay, so I sort of explained what I have talked about, right? So the machine learning for Internet of Transportation. So there are two things, right? One is applying machine learning to improve the Internet of Transportation. Forget about cybersecurity, right? Improve the Internet of Transportation, right? For all the services and so on, right? What the Internet of Transportation is providing. So that you can bring in machine learning techniques. And again, one of the challenges there, as I mentioned, is the ensemble of models, because the Internet of Transportation is constantly changing, whether it's being weather or the traffic. So we need machine learning models that are adaptable. And that is why we need an ensemble of models, the outdated models we throw away and the good models we bring it in. And these models, machine learning models, can also be used for the cybersecurity applications, meaning if the transportation systems are attacked, right? So for cybersecurity as well as for non-cybersecurity purposes. But the biggest challenge that I'm worried about right now is what happens if the machine learning techniques are attacked. And so those solutions I mentioned are all in the experimental stages, whether for transportation systems or even for other systems. And so if we can focus a lot of our research in that area, I think we can really make a truly great contribution to society. So that's what I think we should be focusing on. And it'll be great if we can do some joint work in this area. We will be very, it'll be really good and we can really benefit society. So are there other questions, Professor Nasro Minala? Are there other questions from the audience?
Yes, we have a couple of other questions, but I would like my colleague to please ask question.
Sure. Right, I don't hear anything yet.
Yeah, we're going to unmute her mic.
Oh, okay, okay.
Hello, Doctor. Thank you very much for your presentation. I really appreciate your work. And it's been from the very beginning, you have contributed to the field until now, and that's really impressive for us. I don't know if I can remember well the slide. I think it was slide 15, where
Yes.
there was a dotted line that was in between two classes, a green one and a red one. And
Oh, yes.
If I understand correctly, it is the administrator, I mean the user that is actually working on adding false data such that the classifier is tricked into moving the line on another side, or is it the intruder that actually adds data, or both? Yeah,
that is a very good question, Naya, right? So Naya, right, that's a very good question. So essentially what is happening, there is a support vector machine line, right? So you have the red crosses, they are the bad instances, the green circles are the good instances. What the adversary is trying to do, learning our behavior and trying to move the red crosses towards the green circles, beyond the support vector machine line. So when it goes into the green circles, if you understand support vector machine, they won't be caught as bad instances. That is what the attacker is trying to do. So how is it doing it? It is trying to learn what we are doing. We means are good people, and it's trying to learn what we are doing and pushing it to the beyond the border, the support vector machine boundary, so they won't be caught. So what do? We try to figure out what the attacker is doing, and we try to apply game theory, and then we try to figure out, using mathematical computations, where do we move the line? What is the best place to move the line that will catch as many bad instances as possible? Of course, if we move the line far enough, we can catch all the bad instances, but that's not good, because the good instances will also show up as bad instances because it's going to be below the line. So our challenge is to try to find a location where we can move that line. You see? So that's the challenge. Now, there are some criticisms because they say it's a lot of theoretical work. Is it going to really work in practice? So maybe today we really need a lot of work to do. It's just like applying game theory. A lot of countries are now applying game theory to come up with strategies. Even strategies for war, they are applying game theory. So what I'm saying is we really need to do research in this area so that hopefully, eventually, we can find some good solutions to make it really work, right? So right now, we are not there yet with respect to coming up with these good solutions, but we really need. So this is a very good area for new research if you are interested. There's a lot of opportunities in this area.
Thank you very much, Doctor. I appreciate your answer.
Thank you for your question, Naya. Are there other questions?
Yes, we have questions, but we are now its time is up. So I think we need to conclude the session, and I will request my dean to kindly conclude the session and thank the speaker. Thank you,
Right.
Professor Bhavani.
So,
It was a pleasure hosting you.
yeah, so Professor Minala, if there are any questions, you can send those questions to me, and I will be happy to sort of answer them over the next week or so, and then, you know, and then send it back to you.
Sure, we will. Thank you very much,
Yeah.
Professor Bhavani. Dr. Abdullah, you may take the lead now, please.
Yes, thanks, Professor Nasser. I'm trying to activate my camera, but unfortunately, it's not allowing me to do that. So I would like to thank you, Professor Nasser, for the excellent moderation of this session. I would like to thank Professor Bhavani for joining the Saudi Aramco Cybersecurity distinguished lecture series. I believe she added a great value to this lecture series. She shared an extensive research that you have done over the years. I believe she's one of the key contributors of the cybersecurity domain. And I believe she shared a very important topics today. She, I believe, mentioned the importance of having policy to manage privacy aware. I believe with the machine learning, there is a lot of data that need to be collected, and we need to have this policy to make sure there's no misbehaving or managing of this data. So I believe this very important topic need to be researched with the more increase of using AI and machine learning. And also she mentioned very important, a lot of important topics, but I am highlighting some of the things that also need more research, as she also highlighted, regarding the also the manipulation of data. So the attacker also may trick the machine learning and making wrong decision. So I believe this also another topics need to be researched. And I believe this open a lot of directions for collaboration, and we're looking forward to work with you in future projects. I believe there is a lot of important points that you have raised and need to be investigated. I would like to thank you again for joining us and for sharing your valuable knowledge today. And I would like also to thank the audience for joining us and for their engagement, and looking forward to work with you, Professor Bhavani, in future projects and future talks. And I would like to thank you all for joining us today.
Thank you so much, Professor. And now from Saudi Arabia, I got to switch to Cameroon in Africa, because I give another talk, and that is actually for 2 to 3 hours. So I've got to switch within about 10 minutes. So
that's great. You're contributing everywhere. Thank you.
It has been really my honor, and hopefully, you know, we have a very strong team, and they are also very eager to work with you all. And so hopefully we can have some fruitful collaboration. And we are also very interested in some of your students, to send your students to our university. We had a brilliant student, Yasmin, who was, I think, you know, she's now teaching in a university, I believe, in Riyadh. And so she was one of our students. So she was really brilliant. So if you want exchange students, we will be very happy. And again, thank you. It was my honor. Although I wasn't able to be there in person. Again, thank you very much for hosting me. Thank you.
Hopefully in the future, we'll have you in person.
Thanks. Bye.
Bye.
Bye.